minors project on applying topological data analysis. I'm going to stop my video and do some moving around of things. Okay, can my slides be seen?
Yes, I can.
Great, thank you. Okay, so yes, so I'm Nick, and I'm going to talk about the work I did studying magnetic field lines, 3D field lines, with topological data analysis, which is a tool I'll explain as I go. And so this was work that was done by me and a collaboration between me, Vanessa Robbins, and Matthew Hull. So Vanessa Robbins is a professor here at the Research School of Physics who runs the Applied Topology and Geometry group, which is also in the call today. And obviously Matthew is the current head of the Fusion Plasma and Theory group here at the ANU. So this was a collaboration between two ANU research groups at the Mathematics department and the Physics department, respectively. Okay, so I'm going to just, without further ado, I'll just go. By the way, I am happy to be interrupted as we go if anyone has any questions. And if anyone is interested in the work I talk about, I would be very interested in collaboration opportunities in the future. So if you have any interest in it afterwards, feel free to send me an email. I assume Chris will put my email with the upload of the file. Okay, great. Almost a note. Sorry. Damn it. Slides aren't sliding for some reason. I'm just going to say done. There we go. Now they're sliding. Okay, so as a brief outline of this talk, I'm going to give a brief introduction to that's more motivation. So this will really be intro and motivation. Then I'll give a math background on a tool called topological data analysis. So really we're going to do something more specifically. I'll give a math background on a tool called persistent homology, which is a subset of topological data analysis. Then I'll look at the original example that was done in my thesis, which is what I'm calling orbit classification in a toy tokamak. And then we'll talk about if I've got time, we'll talk about some recent research progress that we've made. Okay, so first of all, I'm going to set some motivation here. So the geometry of 3D fields is necessarily very relevant to fusion physics. So either stellarators or tokamaks in reality. So while this is mostly this is the SPECtaculars program, so this is more about stellarator physics than tokamaks, the underlying interest in 3D fields is true in both of them because real tokamaks will have fully 3D fields, not perfect axisymmetric ones. But one of the problems that we've got is that it's quite practical. It's very easy, well, arguably easy for us to make more realistic simulations of plasma configurations than we could reasonably analyze by hand. So I can either by solving using VMake or DESC for a particular boundary, or importantly, in an optimization code, I'm necessarily running through many different plasma configurations along the way. The tool from my initial configuration, my initial unoptimized state to my optimized one. And the problem is that if I'm interested in the actual 3D magnetic field structure and interested in its, we're going to talk about mostly its topology, the only tools, most of the tools we use to analyze that are going to be Poincare sections. They're geometric tools. And the issue is that Poincare sections, traditionally, you analyze them by making an image of it and looking at it. The problem is that's not a very scalable procedure. So we're going to talk about some tools in computational topology that let us analyze the shape of data sets so that I can pull the geometry of my Poincare sections without actually needing to look at them. And there's been quite a lot of work on this. So this has been, in the last 25 years, this has been developed as a procedure for studying, the shape of data sets. And this has actually been used generically to study nonlinear dynamics. The most impressive example of this is the relatively recent proof that the Lorentz map, the Lorentz system, is actually chaotic. That seems like it should have been an early result, but it is actually not. It was proven in the late 90s and early 2000s using quite powerful computer-assisted tools from computational topology by Kaczynski and others. And we're interested in using these tools to do automated extraction of topological and geometric features from plasma simulations. Okay, so first thing I'm going to talk about, give some motivation on what I'm going for. So here's a 3D field, and I've gone and imaged this Poincare section.
Nick, I think you might be covering the microphone. Your volume just dropped.
So here's a 3D field, and I've plotted its Poincare section, and I'm interested in looking at a particular problem that I want to reproduce here is the question of when a person looks at this field, the very first thing that goes on in their head is they effectively do a segmentation of this space. So you look at this field and you go, oh, I can read off where each of the different regions of behavior are. So over here, I have closed flux surfaces in this region. I can see island chains. There's an island chain here, and I can see chaotic layers. But that's I'm doing that by intuition, not by any formal mathematical procedure. And if I'm doing it by intuition, I can't really get a computer to do it, and therefore I can't really do it automatically. Yeah, if I wanted to do it automatically, I want software that can do this segmentation. So what I actually need is to instead of doing this in my head, I need to work out some procedure that lets me perform the same segmentation of taking one of my field lines and determining whether it's a invariant torus, whether it's an island chain, or whether it's a chaotic layer, using only the information from the orbit. So using only the list of points that the orbit makes with the plane. So this becomes our problem statement. Can I automatically determine the class of a field line, by which I mean, is it an invariant torus, a chaotic layer, or an island chain? And preferably, if an island chain, how many islands are in the island chain. So can I automatically determine the class only from its orbit under a Poincare map, and importantly, only for finite n. So I'm going to do n finite n orbits of my point under the Poincare map. So I take a field line and I follow it. I count n intersections with my Poincare surface, and then I make that a list of points. And I want to use only that list of points to determine what class the field line is. And the objective we're going for is to capture this intuitive segmentation that a person constructs of such a field. Any questions about
that? So you're only looking at one orbit at a time. That is a limitation, or I think.
Yes, I will lift that limitation a bit later, but yes. So yeah, sort of. Okay. At the moment, I'm only doing one orbit at a time. You could probably avoid doing that, but I'm going to do that for now. Because in reality, that's the way the data is obtained. Like if I'm doing field line following, I only get one field line at a time. I can pull them all together into a giant diagram, but I'm, to be honest, losing information as I do that, because I actually know that each of these orbits is different. Okay, so what I need to do in order to do that is think about how I was... Yeah.
Just a quick comment. I mean, maybe you will talk about that, but just in case. So of course, there's a number of methods that have been developed for that, right? Like fractal dimensions, weighted Birkhoff average, Lyapunov exponents. There are many ways.
So they can give me the information. You're right. They can give me the information on whether my orbit is chaotic or not chaotic. They require a bit more information as well. So if I want to do, say, the weighted Birkhoff average for a field line, I really need the whole orbit, not just its motion on the Poincare section. And the other observation is it definitely can't distinguish between a invariant torus and a island chain, because both of those are not chaotic orbits. But the
That's
method,
correct.
but the method
but there are other
methods
can distinguish. Yeah, there are other methods that can distinguish, but it's true that they all rely, as far as I understand, on integrating the orbit more than just points on a section. So, okay,
yes,
it's fine. I just wanted to add the comment.
Yes, that is a good comment. So in this case, how are we going to actually do this? Well, what I'm going to observe is how I am doing this segmentation in my head. What I'm really looking for is partly I know behavior of orbits, so I know that really points sort of bounce around in sort of semicircular loops and move along, because that's how the motion works. But what that means is I'm expecting points to be in little clusters, sort of separated by distances or filling whole toruses. And if they're either in those two options, then I actually know that my different classes of orbits are topologically distinct. So the topological distinction is something I can read off. So if I have an invariant torus, what I know is I'm expecting my points to form one perfect closed circle. If I have an island chain, for example, this one, here's an island, and there's an island you can't actually see that's hidden over here. They're all one island chain. And I know that what I'm looking for is my points forming three little loops. And if it's a chaotic layer, what I'm expecting is some big connected blob. It's a fractal blob, but it's some big fractal structure, fat fractal, which is globally connected. That's an important observation, and has big gaps in it. So it's made of one connected component, but it's got several holes inside of it. Several holes. So that gives me my classification. I just need to count how many connected components each of my orbits is made of and how many holes it has inside of it. Now, how do we do that? Okay. So that you can quite intuitively, so that notion makes sense intuitively. Say if I had to look at one of these sets of points, which is one of the orbits on the Poincare section, and claim that it makes a circle, that makes sense to a person looking at the diagram. Again, it doesn't make sense to a computer, because fundamentally this orbit is really just a list of points. It's a cloud of disjoint points. But it's pretty clear to a person that a cloud of disjoint points can have shape or can have topology. And I really do mean, we're mostly going to go for topology here, but the shape sort of follows. So in this case, I've got a sort of classic example where I've got a blob of points and a blob of points with a hole in it. So there's a hole here, with a void in the middle where there are no points. So what topological data analysis, the tool we're going to look at today, does is make this notion of the fact that a human can see a hole in the middle of this mathematically rigorous, in a sense that the computer will actually be able to calculate it. And the gist is as follows. I take my cloud of points. I'll preempt the thing. The problem that we need to deal with first is that a cloud of points necessarily has trivial topology. It is made of disjoint points and nothing else. If I want to be able to interpret a hole in this, I can't just ask for the topology of my cloud of points. I need to instead make some sort of construction from my cloud of points that has non-trivial topology. What we're going to do specifically is construct simplicial complexes, which are a sort of assembly of triangles, and then specifically make a sequence of simplicial complexes that will encode the connectivity and the topological structure of the data at different scales, where by scales I sort of mean how zoomed in you are on the data set.
Can I ask a question about this example that you have here? So
yep.
Am I right that this example is way fuzzier than whatever you would find in your Poincare section analysis? So is this tool not way more powerful than you need it to be? Because in your Poincare section, you would have either a perfect circle or a fuzzy blob, but not something this fuzzy. Or do you actually need this power?
We can get some, we will need this power. So my perfect circles are, yes, much nicer than this. My chaotic layers won't be. They will be quite fuzzy.
You'll find
so
the
quite,
holes in chaotic layers as well.
Say again?
You'll find the holes in chaotic layers as well?
Yes, that's one of the last slides here.
That is cool. Sorry, I'm going way ahead, but hadn't thought of it. Thanks.
That is one of the things we're going to do. So I know I can look for holes in a cloud like this. So what I'm actually going to do is I'll make this sequence of simplicial complexes, and we'll look at how the topology of the complexes, as the sort of the assembly of triangles, changes over the sequence. And the idea is that if a topological feature is long-lived, in a technical sense, throughout that procedure, that sequence of complexes, then it represents a real geometric and topological feature in the data. Okay, and I will give an example that makes that obvious. So first of all, what do I actually mean by these simplicial complexes, which depending on how much maths you know, you may not have seen. So simplicial complexes are exactly what I've said here, a finite collection of simplexes, where a simplex is a generalized triangle. So a 0 simplex is a dot, a 1 simplex is a line, a 2 simplex is a triangle, and a 3 simplex would be a tetrahedron. These are harder to draw. That's a bad drawing of a tetrahedron, but I mean a tetrahedron. And an abstract simplicial complex then is just an assembly of these. So I'm going to take a bunch of triangles and stitch them together, hypertriangles of different dimension, with a special rule, which is that I want to make sure that faces of a particular triangle are also in the complex. So if I have a line, its faces are the dots at the end. This is a generalization of the notion of a face on a 3D shape. So on a 3D shape like a tetrahedron, the faces of the tetrahedron were the triangles on any side. So there's 4 triangles here. So the faces of this tetrahedron are the 4 triangles. Similarly, the faces of this triangle are the 3 edges. The faces of my line segment are then the 2 dots, and the face of a dot is trivial. So all I'm really requiring is that if I have a triangle in the complex, then all of its faces must also be triangles in the complex. Okay, that's my one requirement. So here is an example of a sequence of simplicial complexes. So I have 3 different assemblies of triangles here, which are actually each inside one of the other ones. So here's an assembly of triangles that's just made of dots and lines. It's just a graph. Here's another one where I've gone and added in this edge. And finally, I've got an assembly of triangles with an actual triangle. So there's a triangle here. Okay. And we're going to basically work with these sequences. The important technical observation here is that these abstract simplicial complexes really are abstract in the same sense that a graph on just made of vertexes is abstract. I'm going to build them from the data set, but they do not need to be embeddable back in the space that the data set itself lives in. So my data sets are all going to live in R2, but the complexes I make will not be embeddable in R2. That's going to be an important technical point later.
What do you mean with embeddable? Like embeddable without self-intersections, or?
Yes, I mean embeddable without self-intersection.
Okay.
So they won't actually look like a realistic. They're not a triangulation of the plane. Is the point.
Okay. So the lines can cross each other many times.
Yes, in fact, they will cross each other.
Like you see on the right there.
Yeah. Yes. So here's a good example where I have a set of specifically the particular simplicial complex we're going to work with today. Sequence of simplicial complexes is called a Vietoris-Rips complex. I'm not using these because they're really the best choice. I'm using them because they happen to have nicely written, reasonably well-behaved software already written to use them, and a couple of nice theoretical properties I want. So the complex here is the idea here for all of these ways of how I encode the connectivity of my data at different scales, which is what I mean by convert the data into a sequence of simplicial complexes, is I take every point and I draw an epsilon ball around it. And if 2 of my points are have their epsilon balls intersect, I connect a line between them. That's what we mean. And I do that for every point and every combination of points. So choose an epsilon and consider some cloud of points. Then this thing I'm going to define as the Vietoris-Rips complex at radius epsilon. Well, actually, it is radius epsilon. Is the complex where I just include every hypertriangle, whereby this set of triangle brackets with the vertexes, I mean the triangle whose vertices are the points xk1 through xkn. Yeah. I include every triangle whose distance from all of whom's distances are less than my epsilon. So that is, I include every triangle such that every pairwise distance is within an epsilon ball. We'll see it has my epsilon balls intersect. And I do that for every point. And so actually, I'll show you the example here. So when epsilon is 0, none of my points none of the epsilon balls intersect with each other. So none of my points, I don't add any edges, because if I have a 0 radius ball around this point and a 0 radius ball around this point, those 2 balls don't intersect. So I don't add the triangle. I don't add the edge. Eventually, I am including balls big enough that there will be some intersection. So I add an edge in. And as I keep increasing epsilon, so epsilon goes up in this direction, I slowly add edges connecting points that are further apart. And eventually there will be a point where I have 3 triangles, three balls, each such that every point is actually mutually within the epsilon radius of the other points. And at that moment, I fill in the triangle. So that's when I get this little triangle appearing here. And as I keep increasing epsilon, I add more and more and more triangles, and eventually add, like there's a tetrahedron here. Eventually, if I take epsilon big enough, like that big, every point will be within epsilon of every other point. So actually, every point is connected by an edge, and every collection of points is a triangle. So that's why I say this complex will definitely not be embeddable in R2, because at the end, I at least include, if I have n points, I at least include one n-dimensional triangle. And that definitely can't be embedded in R2. But the interesting observation, and the important observation technically, is that as I increase epsilon, each of my complexes is a subcomplex all of the later complexes in the sequence. So this set of dots is a subcomplex of this one, and it's also a subcomplex of this and a subcomplex of this, and that's always true. So each complex in the sequence is included in the later ones, and therefore they actually come equipped with inclusion maps between complexes earlier in the sequence into the ones later in the sequence. Those inclusion maps are okay. So this is our main tool. Well, we're going to use this to do a thing. So this gives me part one that I need. This gives me my way of converting my data into a sequence of simplicial complexes. What I now need to do is part two, which is I need to actually be able to describe the topology of my complexes at each stage. And I can do that with a tool from algebraic topology called homology. So homology is a topological invariant, and it corresponds effectively to counting the number of n-dimensional holes in a space. So a hole, what we're talking about here is, I'll do this example. Okay, so as a note, 0-dimensional holes are connected components, just as a note on the convention there. So here's a torus, and a torus has two 1-dimensional holes in it. There's a 1-dimensional hole in the center, and there's this 1-dimensional hole that's sort of the void in the middle of the torus. I'm just talking about the surface of the torus right now, not the donut, not the filled-in donut. And the idea of homology is you detect that those holes are there by looking for loops on your surface, basically, that are closed, but not the boundary of something. So in this example, I've got this blue loop here. It closes on itself, so it has no boundary. That's what it means to be closed. And an actually closed loop will have no boundary. But because the torus is, because I'm only considering the surface of the torus, there's actually no space in the middle for this. There's no surface in the middle for this loop to actually be the boundary of. So that's what I mean by it is a hole. By contrast, this green loop, it is closed. So this is a loop on the surface. It is closed, but it's the boundary of this green region. And that's what we interpret as meaning is not a hole. This is just a loop that's doesn't represent a hole. And similarly, I can do this internal, I can also do a loop that does this that does the hole in the center of the donut as well. So the loop along the center here is closed, it closes on itself, but it's not the boundary of anything because there's no surface in the middle of the space.
Okay. Can I ask a quick question? So from what I remember from topology, the way to count holes is via Euler's formula. Like it's just a very simple faces minus edges plus dots or something. Is that
so
what's
that
going
does
on
let
under
you
the
count
hood?
holes? That does let you count holes, but it's a less sensitive invariant.
Okay.
So you can count holes like that using the Euler characteristic, and in fact, it's very closely related to homology. The Euler characteristic, I might state that later. I won't prove it now. This thing we're talking about here is a much more sensitive invariant that can capture more hole structure. So yeah, that sort of gives you an integrated count of all the holes. Okay. So now we can also do this. So I'll do as another example, this little one here. So I've got a simplicial complex here, which you can think of as a space in the same sense. And it's got two holes in it, and it's made of one connected component. So that's what I mean by this. And those two holes correspond to this loop and this loop. And the connected component, I won't point out exactly where that's from, but it is from the right spot. Okay. Now, the way we actually then do this, homology does this. So the Euler characteristic example assigns a number for the number of holes. Homology does this a little bit differently. And instead, we assign a family of abelian groups. So they're called HN. So N being the end dimension. So the H0 will be 0-dimensional holes. The H1 is 1-dimensional holes. The H2 is 2-dimensional holes. So we're going to assign a family of abelian groups where each of the generators of these abelian groups will actually represent a topological feature. So as a note, you can think about these abelian groups because of the way we're going to set this up in the context we care about. These are really vector spaces. And by generators, I'm talking about basis vectors. So I'm going to assign a family of vector spaces whose dimension is the number of holes in the space. And each of the basis vectors will represent one of the holes. Each of the basis vectors are one of the loops, effectively. So for this case, my vector space is Z2, which you can think of as a vector space in this context. And my for the zero case, because I've only got a zero-dimensional hole, one zero-dimensional hole, because a zero-dimensional hole is a connected component. I've got one connected component, so there's one copy of Z2 in as my vector space. Here, I've got two one-dimensional holes there, so I've really got a two-dimensional vector space here for the other two. It will be clear why we use Z2 in a second. So to make this actually formal, we need some maths. So suppose I've got a simplicial complex, then I can actually construct a family of abelian groups that I'm going to call the chain groups that represent these loops that I'm drawing. So I'm drawing loops, but I'm not going to actually think about them as paths on the surface. I'm going to think about them as formal sums of the edges. So this loop I've just drawn, so call this edge 1, this edge 2, and this edge 3. I'm going to think about this loop I'm drawing here as actually just being the formal sum of these three edges. That's the loop. Okay. So, and importantly, I can actually construct a whole group or a real vector space by taking the edges in my diagram and well, the nth dimensional triangles as the generators or the basis vectors for my vector space. So I just take each of the n simplexes, so each of the edges of each of the triangles of a particular dimension, and I add them all up in a formal linear combination. So I just make a vector space out of them, with them being the basis vectors. And at the moment, I'm going to specifically do the very lazy thing of assuming that the coefficients are Z mod 2. So they're all either 0 or 1. That will turn out to be basically sufficient. And it's mathematically nice because it means I'm making a vector space over the trivial field. Well, the smallest non-trivial field. The interesting observation is that we can construct what's called a chain complex. So I get, as a note, so I get one of these vector spaces in each dimension. So there'll be a C0 made of formal sums of the vertexes. There's a C1 made of formal sums of the edges, and there's a C2 made of formal sums of the triangles, plus ... But they're not wholly independent in a meaningful sense. So by that I mean they come as a sequence where you can reach each vector space from the other with a linear map between them. These linear maps I'm going to call del n, they're the boundary. And the boundary map is defined by summing codimension 1 faces of an n simplex. Codimension 1 means a dimension less. So the diagram here is more explanatory. So here I've got an edge, and I want to compute its image under this, what I'm calling the boundary map, del. And the boundary map is effectively what you might think it is. It's meant to be an algebraic version of a boundary. The topological boundary of my edge would have been the 2 points, really interpreted as a union. I'm just going to make the formal sum of the basis vectors for their associated chain. So here I'm going to get the boundary of my little one edge is the 2 vertexes. The boundary of my triangle, I'm talking about the triangle here, is the sum of the codimension 1 faces. Well, my triangle's faces were the edges, so I make the sum of the edges. And similarly, if I've got a triangle, this is the triangle without the, I'm talking about the loop here, not the actual, not the triangle in the center. The boundary of this is the boundary of the faces of the boundary map on each of the 3 edges. So this becomes the boundary of this edge, plus the boundary of this edge, plus the boundary of this edge. But each of these boundaries is actually just the vertexes on the ends. And the observation actually is this is why one of the reasons we chose Z mod 2 coefficients. 1 plus 1 equals 0. So that's 0, and that's 0. So the boundary of this little loop under this special boundary homomorphism where you take formal sums of codimension 1 faces, if I have a loop, its boundary is 0. In fact, this is a very famous observation. This is the sort of fundamental theorem of homology, that boundaries are always closed. So if I take any chain, any simplex, any formal sum of edges, I take its boundary, that gives me what you might interpret as it should be topologically the boundary of something. And it should be therefore a little loop, because I'm talking about sort of real sums of closed spaces, their boundaries should be loops. And then when I take its boundary, I find that that is always 0. And this means I can actually use this boundary notion to measure closure in a meaningful sense. So I wanted this notion of what it means to be closed, but not a boundary. Well, closure means I evaluate to 0 under the correct boundary map. And not a boundary means I'm not the image of something under a boundary map. So this lets me make my final definition here, that a hole in a space is related to a chain, so the chains are the formal sums of simplices, which is closed but not a boundary, and we'll call these closed chains cycles. And we formulate that as a quotient group. So the kernel here is any chain that gets mapped to 0, so it's anything that has no boundary, and the image is everything that is a boundary. And I'm going to make this quotient group, or it's a quotient vector space. These I'm going to call the nth homology groups, and they measure the topological structure in each dimension. So an important observation is this is a quotient group. Quotient groups are spaces of equivalence classes, not spaces of classes of objects. So I'm specifically going to have here, if these are equivalence classes, then there needs to be an equivalence relation. And the equivalence relation is actually that two chains, two loops, are the same if they differ by a boundary. So I will do the diagram here that elucidates this. Here is a torus again. And I'm going to draw I'm going to consider this loop. Consider this to be C. And another loop, I'll do this one. Yeah, so here's another loop that I'm going to think of as C prime. So these are both closed loops, but they represent the same hole. And they represent the same hole because they're members of the same equivalence class in homology. So they each generate one of these classes, specifically in H1. And I know they're the same equivalence class because the difference between them is this blue region I'm shading here. That is, this C prime looks like C plus this boundary on it. Their difference is the boundary of this little green region. And that's what it means to be the same in this context, is you're in the same class if you are different by only the boundary of a higher dimensional chain. Any questions about that at all? That's a very short introduction to quite a subtle thing.
I think quite a lot. That was quite some deep math, but just from a high level, like you're talking about this with groups and with fundamentally, when you implement this, what you're doing is you're still gonna like computationally, you're gonna like, why do we need all this powerful terminology? Is there another way to see this without homology groups, or is this
That's a good question. I'm going to say no. And to be honest, the reason we need this is because of the theorem that's on the next slide. The fact that we need is that what I want to be able to do is track throughout this sequence. I want to be able to track the evolution of topological features. And in order to do that, I need the useful fact is what's hiding here. So what I want to be able to claim and point out is that this hole here is the same as this hole. They're the same feature. That lets me track the evolution of topological features. And the way I'm going to do that is by looking at the class that is represented that represents this, the homology class that represents this hole. And I'm going to associate to this sequence of complexes a sequence of maps between all the complexes that induce maps between the homology groups. So I can say this hole is the same as this one if it is the image under this induced map on homology of my class. So if they map to the same thing, then they're the same class. So I need that structure, this fairly complex algebraic structure, in order to be able to track the evolution throughout the sequence, which is what we're going for. And you'll see why that's what I'm looking for. Okay, so the fact that we need here, so throughout the filtration, the homology of the complex is going to change as I analyze the data set in scales. And I'm interested in what we're going to do is persistent homology here, where I want to track this change and record how the topological features change as I move that. Because if a feature represents something is a long-lived topological feature in this sequence, then it probably represents a real feature in the data set. That's the sort of fundamental axiom. It's the motivation. And so therefore, I need a way to track the evolution of individual topological features, which I can do by tracking the evolution of individual homology classes. Conveniently, this is possible because of a fact about homology, a special algebraic fact because of a structure called functoriality. So what this means is that if I have two spaces and a map between them, then the homologies of those spaces also come equipped with an, so this is the map I, also come equipped with an induced map I star, that's terribly drawn, I star, H star Y. Yeah, so they come equipped with an induced map where the evolution of class, the image of classes under this map tells me something about the topological distinction between the two spaces. And importantly, from my sequence of classes of complexes before, I had these inclusion maps between them because they're all included in each other. So each of those inclusion maps generates a map between the homology of K0 and the homology of K1 and the homology all the way up. So I get this sequence of homology groups joined by maps. And the observation is that a topological feature exists, if a topological feature exists at some stage in this filtration, this sequence of complexes, and then stops existing later, then it will actually be annihilated by one of these maps. The class representing it will be killed by the map. It'll be in the kernel of one of these induced maps. So I can define a class to persist if its image under the induced map is actually is non-zero in the next homology group in the sequence. And it dies if its image is zero. And similarly, I can say a topological feature is created at a stage if it exists in a homology class, a group, and didn't exist in the previous homology group, by which I mean it's not the image of a class in the previous group. Okay, so I will now do an example of this. So the point is, here I've got a sequence of, well, this isn't my example, but yeah. So here I've got a data set, and I'm doing this procedure of slowly connecting points as I increase radii. And at every stage, we're computing the homology in each dimension. So this is the H0 homology and the H1. And so each of these bars represents one of the classes. And as I evolve forwards, eventually these lines, so this line eventually gets, well, one of these lines eventually gets created. And that means this class will have been, it is in the image, is in my very small radius homology groups, but it's not in the image of one of the induced maps. So it actually gets killed, by which I mean I end this bar. So this is what we call a bar code. And it says, I can now run through all of my classes and I can say when they're born and when they die. And that gives me the lengths of these bars, basically the points in the little sequence. So the best example I have is this one. So here I've got a data set and I'm increasing epsilon, the little radius of the Viator-Thrips complex. And I'm slowly connecting up more and more and more points. So classes will be born at some diameter and they'll die at some diameter. These should be radius, sorry. It doesn't really matter, but I'm going to go with radius. I probably should be diameter. There's a technical distinction. The set of these birth and death pairs is what I'm going to call the persistent homology. And we're going to basically turn them into a little diagram. So what you observe here, initially in this case, I start with a whole bunch of disconnected points. So my homology says I get a zero-dimensional homology class for every connected component. Well, if I've got n points and I've got n connected components, then I should have n classes in my homology group. So back here, my homology group is just going to be Z2 to the number of points. Right at the very, very, very end, I'm going to have one connected component because when my radii are really, really big, all my points are connected to each other. So I'm going to have Z2 to the 1. And as I slowly increase, I should expect that classes are killed. So I start with a whole bunch of bars and I end with one bar. So presumably one of these has the full length and the others die at different times. So I can sort of draw on the barcode here. The interesting feature in this particular data set is the hole hiding in the center. So obviously this is a sort of looped data set. I made it that way. And as I go along here, there is a particular point at about epsilon equals 0.8. So initially, there won't be anything in the one-dimensional homology, at least anything non-trivial. But at 0.8, a class is born when an edge is created here. This edge forms a loop. So I can run my points around here, and I can make this loop. So that represents a hole. And actually, it's the same hole as later on here. So that hole actually eventually dies at about 1.4 when I fill in this triangle. So this hole that I have seen is born at about 0.8 and it dies at about 1.4. So B is about that and D is about that. So it's got a persistence, a lifetime of about 0.6. That's quite big. So you would probably argue that the existence of this pair, this birth-death pair, represents a real topological feature in the data set. And it really is. There's a real hole in the data set. And the way you see this is you compute this homology evolution at every stage, and you work out when each class is born and when it dies. And you go and plot them all on a little diagram. So here's my point. Here's my little scatter plot called the persistence diagram. And that class, the one that represented the real topological feature, is this big dot here. So I can now, by looking at this data set, by looking at this persistence diagram, I can see that there is a big single hole in my data set. So big single holes are represented by long-lived, and long-lived means this distance is big, long-lived homology classes in H1. So I can read off the topological structure of my data set from this diagram, at least up to some level of noise sensitivity.
What about the, sorry to interrupt, what about the long-lived blue dot on the top?
So there will be a very long-lived blue dot. So blue is H0 here, its connected components. One of the connected components lives forever because at the very end, the data set is connected.
Yes, no, I meant the other one, the next one, which is also 0.6.
Oh, that's that one. That is, I think this point, roughly. I think that's the longest edge in the diagram. Yeah. This is just, so these represent the connected components. So this tells me that at least one of my points is quite a long distance from the others.
I see.
So this can actually be used as a clustering scheme. This information over here, by the way, this, if you know anything about clustering algorithms, the information in this H0 persistent homology, what I'm going to call that, is equivalent to computing a minimal spanning tree and further equivalent to something called single linkage clustering. So you can actually use this to infer the clusters in your data set if you want. That's actually one of the things I'm going to do in this talk. Okay. But I'm going to be more interested in the first persistent homology here. It's the thing that I care more about. So it's loops. So these are connected components. This is loops. Okay,
Nick, I do want to mention, I see you have 44 slides in total, but we are
a lot of them are
running out of time.
Yeah, I know.
If you want to go through all of them. So we have 10 more minutes before we start.
We did start 15 minutes late, but sure, okay.
Yeah.
I'll try to run through this. So one observation you might make here is that so what I can now do is I say a particular data set is, so a particular feature is, a topological feature is represented by one of these classes, and I could define them to be real topological features if their death minus their birth is big. That turns out to not be always the best choice. So it's a choice of statistical significance. There is an alternative, which is what I'm going to talk about now, which is to do, oh, damn it, this thing is, I've had struggles with it. The other option is I use the ratio of death time to birth time. So here I've got a loop made of, a sort of hexagon made of 6 little loops. And if you were to compute its persistence diagram, so that little graph from before, you find that it looks a bit like this. So I haven't included it on the diagram, but it looks like there's one really persistent class and then like a couple of little dots that aren't persistent. The one really persistent class is the fact that it's a hexagon. The 6 little dots are all the little loops, but if you were to use this as a measure of statistical significance, you would basically see this as equivalent to just 6 points, which is sort of something I don't prefer in the context because of what I'm going to do later. Because island chains look like this is why I care about this distinction. But if I use the ratio of death time to birth time, which is what I'm displaying here, and I'm putting it against the death time because that gives me a measure of radius, I can see that I get one class with a sort of ratio of death time to birth time about 2. That corresponds to the fact that it's a hexagon, and I get 6 classes with a even bigger ratio of death time to birth time that correspond to each of the little loops. So if I have a data set that I know is made of lots of little loops, this epsilon death on epsilon birth is actually a better measure. And it's what I'm going to sort of mostly use. Okay, so we can now talk about how to do automated orbit classification. Now that I have a procedure for working out the topology of a data set, I make this sequence of complexes, and then I compute the homology at each stage, and I look at how the and I can effectively compute this little diagram. So I compute the birth and death time for all the classes. I can now actually do this for my Poincare sections. So take a finite time orbit. So take a point on the Poincare map and look at the point cloud generated by running the field line t times. I'm going to claim that the persistent homology of this point cloud encodes information about the topology of the orbit. And specifically, we want to write a list of criteria using only the persistent homology, so using only the diagram or this set, which lets me specify which class the orbit belongs on. So whether it's an island chain, an invariant torus, or a chaotic layer. Yeah. So let's do that. So I'm going to do that for a toy model of a tokamak device. So I'm just going to look at some data now. So this is my favorite little toy model of a turb tokamak, which is just made of 2 currents. It's not really a tokamak, it's sort of reverse. It's reverse shear actually, but it does have the feature I want, which is that it has it's axisymmetric until I add a small perturbation. So it's made of an infinite line current and a circular current. And if I add a small perturbation to the position of the line current, I'll create chaos. And we're going to play with that. So here I have one of my orbits, and this is its point cloud. And I've computed the H1 relative or multiplicative persistence diagram. And it's got one class that's at sort of relative multiplicative persistence 60 and a whole bunch of nothing. This one class relative persistence 60 is the fact that this is all a giant loop. And it actually corresponds to it really corresponds to the fact that this is closed in the poloidal direction. That's an important observation. Because it's closed in the poloidal direction, and it covers a poloidal ring or a poloidal annulus, at epsilon equals 0, I basically instantly get a class created corresponding to a lap around the poloidal section. And that only gets killed when I choose my epsilon big enough that I can sort of cross an equilateral triangle around the region. So I'm basically guaranteed to have a class that is born at about 0 and dies pretty late. In fact, it'll be the last class. The overall colloidal structure is the biggest circle in the set. So here we observe that fact. Okay, let's look at a different case. Here's an island chain. I've now taken the same observation. So we've now got we've done the same thing. I've run an island chain. It actually is an island chain. I haven't run it for long enough to go. And you see a couple of things. One, there's now these 4 nice points. Yeah, those 4. Those are the actual islands. There's actually 4 here. There's actually 2 points here. There's 5 points. So there's 1, 2, 3, 4, 5. It's failed to detect this one as a significant class. I will deal with that in a second. And there's also this one quite large. Actually, sorry, I'm doing that wrong. Sorry. The relevant 5 classes are these ones. And there's also one class corresponding, again, to a poloidal ring. But because my islands have non-trivial gaps between them, the birth time of the class corresponding to the poloidal ring, to this sort of loop, is bigger. And in fact, it's much, much, much bigger. Previously, this ratio of death time to birth time was about 60. Now it's about 2. That's going to be a useful observation because I can look at, say, a stochastic layer. And here, again, I get lots of noise here from the many, many, many different internal holes. We'll talk about that in a second. But I still get this one persistent class at very high death time. It corresponds again to this loop I can always draw around the poloidal ring. But because the stochastic layer is actually closed in the poloidal direction, the birth time is again really small, and hence this ratio of death to birth is very high. So this actually gives me my first little criterion. I can distinguish an island chain from all of the other orbits by just looking at the death over birth of the last H1 class. And if that is bigger than some threshold, I call it if it is smaller than some threshold, I call it an island chain. If it is bigger than some threshold, I call it not an island chain. That's our first little check. So I call this the enclosure of the orbit. It's the death over birth ratio of the last to die H1 class, so the biggest feature. And if I go and pick a threshold, which happens to be 20 here, and run all of my orbits from before and color them based on whether they are above or below this threshold, you can see that it actually does the correct thing. It picks out the islands. So all of my invariant toruses get colored red. All of my island chains are colored blue. And the stochastic layers are also red. So I've now got an island identifier. That's great. Cool. So that's our first big thing that we're really happy with.
Quick question. The threshold, of course, is somewhat arbitrary and picked by hand. So how do you,
Yes.
you know, is it somewhat universal? I mean, can you choose a threshold always for any field and it will be okay? Or, you know,
So
the usual question.
It's a good question. It's one of the problems that's pointed out later. There's two ways you could get. One, you could work out, given your, basically, the threshold determines how closely packed of an island chain I will detect as an island. So it affects my sensitivity, effectively. If I set the threshold as lower, I'm going to be more and more and more sensitive, but I'll probably start to misclassify things. So you get some design freedom there. And if you know, perhaps, that I only care about island chains with an M number up to, or an N number up to 100, then you could probably sort of take a radial disk and ask how far through, take a colloidal surface and ask how far along do I actually need to be to fit. If I'm going to sort of equally space 100 islands along, how far apart will they all have to be? And that you could use to fit your threshold, because it tells you the depth time that you would need, and therefore tells you this. The other way is you can infer it from the data. So here I've plotted this enclosure across all the orbits. And what you notice is that it's got two levels to it. So there's a bottom level and there's a top level. So if you were to plot the histogram of this value, you'd see that it's in two clusters. So you could use clustering to split those two and find a value in the middle. So you can see the two levels here, because we've got a bunch that are basically 0 and a bunch that are not 0. And you could infer that from the data if you want. It's not universal, though, although it will be more interesting. Okay. So I'll now talk about some recent research. And first problem. So the nice thing is that actually makes this more powerful than the older methods. So there's some older methods from, or just pure theory, but there's also some tools from Yip and others from the 90s for doing Hamiltonian orbits like this. The problem is that often you can't infer anything about internal islands. So here I've taken a chaotic layer, and it's blatantly obvious to a person that there is actually a bunch of islands here. But the orbit actually isn't on those islands. And if you were to say ask for, and obviously my previous detector won't see them. And well, it shouldn't. This actually isn't an island orbit. And if you were to ask for sort of pulling, if you were to ask whether this is a chaotic orbit or not by something like the weighted Birkhoff average, you would actually find that it is chaotic. So you don't see, all the standard methods don't see the islands in here because they don't have a way of observing voids that are in the point cloud. By the way, it's not surprising that you get these, the fact that these islands stick out really funnily is because islands are sticky. So at one point, the chaotic orbit got really, really close to this island. And when it gets close to islands, it has to stay close to islands for a really long time. So because islands are sticky, you do get this sort of black banding around the islands. But that's not the only problem. So if I was to take this current, so what I want to do is count these internal islands. So basically, I want to infer the structure about voids from my classes. But one of the problems I've got is that some of the islands aren't going to get detected. So I can go looking for these voids, and they will show up as classes. But they're going to have problems when I'm really close to the inboard side, because the field strength is really high, and therefore the islands get really small, because they're preserving, the Poincare map is preserving of the flux, not the, well, to quote Stuart, is preserving of the flux, not the actual area. So the problem is that this actually isn't, I should expect them to get really thin where the flux is, where the field strength is high, because in order to keep the flux the same, the actual, the geometric size would have had to be smaller if there's high field strength. So what I would like is a way to fix that. So currently, if I was to get my systemology to count this, so if I was to do this problem, God damn it. If I was to do this case, I see one interesting, so we do see a persistent cluster. So here's the data set for this particular case. I see one class corresponding to the same global poloidal structure, and there's 5 or 6 classes here that correspond to the islands internal to the orbit. But I don't see all of them, because you can count how many islands there are here. I believe there's 13. But I'm only seeing about 5. And that's because a whole bunch of them are too thin to be realistically detected as holes. They're very, very narrow. So the question is, can I fix this? And the answer is, well, yes. The problem is that I'm not in the right coordinate system here. So this is in physical coordinates, but let's unfold into straight field line coordinates, which is what I've gone and done. So this is in straight field line coordinates. Don't worry about the little hump here. That's a numerical problem. This is close. It's not actually, it's almost the straight field line coordinates. It's close enough for our purpose. And all of those really, really thin islands have been unfolded into non-trivial little loops in straight field line coordinates. So I can now actually do the persistent homology in straight field line coordinates. And in fact, here you might notice something. You might notice all of these little holes as well. It's perhaps not obvious, but they're actually also an island chain that's really subtle in this particular chaotic orbit, but there is actually a second island chain embedded in it. And the persistent homology will pick that up. So one of the problems I've got, though, is that once I'm in straight field line coordinates, so I'm in what I'm calling J, although you could call it psi if you wanted. It's the psi p if you wanted. It's the, I'm calling it the action, because I like to think of these as action angle coordinates. But this necessarily needs to be a cylindrical phase space. That's what's going on here. When I'm in action angle coordinates, I'm on a cylinder. And so I can't use the physical metric that I had originally. So I have to measure distance in order to complex. And therefore, I need a notion of measuring distance. Previously, I could use the actual distance in real space, but I can't do that here. I'm not on real space anymore. So I have to just sort of arbitrarily equip the space with a metric. Because this is a cylinder, and therefore it's a manifold, or it's a Riemannian manifold, I can actually just do that by literally equipping it with a metric in the differential geometry sense, and then doing geodesic distance. In this case, I'm doing the trivial metric. So I can, for any point, really this asks for the sort of the curve from them that runs along the surface of the cylinder. So that's the metric I'm doing. And that's actually what the coloring is, by the way. The coloring is meant to demonstrate the periodicity. So there's a point here. I think the point's actually here. And the color is the distance of every other point from this point. And the observation is that points over here are actually close to points on this side. Yeah. So they're the same color. Okay. So that is the performance in straight field line coordinates then should actually be much better. So previously we were undercounting the holes. Now we don't undercount the holes. So we still have the same class up here corresponding to the global colloidal structure. That's now really a loop running around this cylinder. But I've also got this set of 13 little dots. They are the cluster corresponding to the main island chain here. So they're this set of 13 orbits. There's also this sort of cluster here. We'll see a little bit later that it's actually these extra very subtle islands. So some of these are noise, but most of them are the subtle islands. So you could actually really wanted to extract individual island chains. Something I haven't done yet, but would be an interesting thing to do, is to run clustering. So take a particular chaotic orbit and actually run clustering on this persistence, well, this death over birth ratio diagram I'm making to extract each of the individual clusters. So this I would think of as a cluster, and yeah. Cool. So that's one idea. So that's some very recent research where we've gone and fixed this undercounting problem. Once we're in straight field line coordinates, the undercounting problem goes away. And I can actually now do some other useful things. So now that I have a actually useful notion of how to count, of the fact that we can count, we can go and ask a good question, which is, can I use this for anything other than just classifying my orbits? And I'm going to talk about measuring integrability here. So it's interesting to ask, what does it actually mean in the fusion context for our field to be integrable? Well, you could be technical and say that it means there exists action angle coordinates for it, and I would argue that's correct. But it's also realistic and quite reasonable to just say that the field line orbits generate a foliation of the phase space by circles. So the phase space was that cylinder from before, and I'm going to foliate it by, and when my field is integrable, it's foliated by circles. So it can be thought of as the disjoint union of all of the circles. And each of these circles is an orbit of the field. Well, really the closure of an orbit with the field. So here I've got I've got an integrable version of this field. So when I set that little shift parameter to 0, and I've got that same thing in straight field line coordinates, and it becomes this nice set of nested, of layered circles. If I have a non-integrable field, that's obviously not true. So I'm going to have many, not all of my orbits will be nice nested circles. So this field, the orbits do not foliate the phase space with only circles. They do generate a foliation of the phase space, but they're not a foliation by circles. So what you might note, though, is that all of these circular orbits in my phase space have identical persistence diagrams because they're all exactly the same. At least in straight third line coordinates, they're all exactly the same. So here is the persistence diagram for all 21 of those orbits, and I've unioned all of the persistence diagrams. So there's 21 persistence diagrams, and I put them all together. And all you see is 21 dots, plus some tiny bit of noise. Don't worry about that. 21 dots all stacked on top of each other, because these are all topologically identical. So really, there's just a single class who's born at 0 and it dies at 2 pi and 3. The 2 pi and 3 is to do with the structure of Vietoro's complexes and the fact that I'm doing geodesic distance. It's not important. The point is that I know what the persistence diagram, or the union of persistence diagrams, for all of the orbits of an integrable field looks like. So the question is, if I take a particular field, so if I take any other field, though, I don't get the same structure. So here I've slowly increased the perturbation strength, and you see that the persistence diagram changes slowly from this really trivial case to a very non-trivial diagram where I have a couple of classes in the original spot and other things moving around. So I'm still doing the union of the persistence diagrams for all of the different orbits. That's why it's a combined persistence diagram. So the question is, I can see that as I increase my perturbation strength, these diagrams move, in some sense, further away from the integrable diagram. So the question is, can I measure that movement? And the answer is I can. Specifically with another tool from topological data analysis called persistence, called Bohlsen distances. So the one advantage of persistence diagrams, specifically over my little death over birth ratio plots, is that it's actually possible to ascribe a notion of distance between diagrams. So if I've got two diagrams, I can actually I can make a metric that describes how far apart two diagrams are. The metric is called I'm doing Bohlsen 2 here. It's one of the metrics. There's actually a couple, which is defined as follows. So I've got a persistence diagram, and I'm considering matching functions that identify classes in one persistence diagram with classes in another persistence diagram. I'm computing the 2 norm the square of the 2 norm of the distance that I move all the points in the persistence diagram when I do the matching. And I look for the matching with smallest total length. So smallest total 2 norm. That defines the Bohlsen distance. And it's actually a metric. And we can use it, therefore, to measure how far a particular field is from integrable. So if I consider a sample of initial conditions and their orbits, then what I mean by foliating the phase space is that I think of the Poincare section as made of a disjoint union of the closure of all of my orbits. So here, I had my phase space I would think of as the disjoint union of all of these circles. Nice fact about persistence homology is that if I have a disjoint union of spaces, the persistence diagram will be the union of the persistence diagrams of each of the individual spaces. So this justifies why I was combining the diagrams before. So if I think about my phase space as this disjoint union, then I can compute this union of all the persistence diagrams as its own persistence diagram. So this is actually a persistence diagram. And I can compute the distance between this diagram and the ground truth, the trivial one. So this is the trivial diagram. So I can ask then, how far is the persistence diagram I get from my field with some amount of perturbation from the case with no perturbation? And I can actually plot it. And you see, this is very preliminary. You see that it actually does what you would expect. So here I'm increasing the perturbation strength, and the value of the amount of chaos, the distance from the integrable diagram goes up. It actually goes up very quickly at first, and then it sort of slows down a little bit. And it should plateau sort of roughly here because you pretty quickly sort of saturate with the amount of chaos that you can get. 0.1 is quite a large perturbation strength in this context. So this does appear to do what I want it to do. So I wanted a global measure of the distance from integrability that takes in a whole field and tells you how far it is from integrable. And this can do that. So if I take a particular, if I take a field, I can go and compute this. I take some number of orbits, and then I union all their persistence diagrams, and then I compute how far that big union is from the trivial diagram. And that gives me one of my points on this little curve. But yeah, this is only preliminary evidence. The interesting observation, because there's other ways to measure how integrable you are, but this is a global measure. So here I've done the entire field as a whole, not just how integrable is a single field line, or what's the total area of chaos, which would have been the other thing you might have gone for. There's some to-do going on here. I still need to characterize this function. I haven't really done that. This distance function. I need to investigate how the convergence behaves when you have longer orbits and more initial conditions. And what I actually want to use this for is as an optimization target. So I want to use this as an optimization cost to take a field and sort of seek the nearest possible field, the smallest perturbation I can make to it that restores approximately restores the integrability of the flux surfaces. Okay, so at this point, we're really out of time, and I've now effectively shown that, using TDA, we can actually automatically detect the class of magnetic field lines in a nearly integrable 3D field, and we can measure the non-integrability in a global sense, which is new. So doing this globally is sort of new. It requires only the orbit of the field line on the Poincare section, so I don't need the intervening information. It's probably worth having the intervening information, and you could learn things from it. I just haven't done that yet. I also don't need the order that the points arrive. That is an interesting observation in this context, because the order shouldn't really matter. But there's a couple of things dealt with here. I really haven't dealt with how small a number of points you can get away with, which would be about computational efficiency. And I need to characterize this integrability measure. Okay, thank you. That's the official end of the talk. I'm now happy to take questions in whatever time's left, and I have a couple of extra slides if anyone wants to see them.
Thank you very much for a very beautiful, impressive talk. I first want to open the floor if there's anyone who wants to raise their hands or has a question, but I myself have several.
I'll just turn the camera back on.
No
one
raising their hands. Then I'll, I don't think we should go too long because we're already 15 minutes over the hour, but I had one question. So for the final measure of chaos that you arrived with, did you need to use the straight field line coordinates in order to get a proper resolution, or did that also just work with, because I can imagine that that's a little bit harder to do in a stellarator context than with the toy model that you applied it to?
Yes, so I did this in straight field line coordinates. That was probably not necessary. So you could do, so the observation that I really need is just that all the persistence diagrams look roughly the same, or more accurately that I can write what the sort of ground truth diagram is. If I...
And do you need the ground truth to be present for this, or is there is a universal shape of the ground truth so that you don't need to, like, if you apply this to stellarators, you would want to have like a closed by integrable field to compare to, or do you not need that because you know?
So that is why I sort of want field line coordinates, because then there is a universal. The universal is this one.
It is at 2π/3 because that's just a property of your.
It's because the phase space has to be a cylinder, and the phase space has to be a cylinder because that's what Hamilton-Jacobi theory says it has to be. But it's probably not necessary. So you could do, you could just imagine what a diagram looks. So to be honest, I'm not sure. Personally, I want this in order to build. What I want to actually do is use this as to say I've got a Hamiltonian, and that you can imagine as a field line Hamiltonian for a 3D field, for a stellarator. And what I actually want is to find, so the problem is that in order to get my classification to work well, I actually need to be in straight field line coordinates of a nearby integrable field. So what I actually want to do is work out how to take a field and find a nearby integrable field. So you go and parameterize the action angle transformation and a perturbation to the field, and you seek a new Hamiltonian H double prime, I guess, such that the coordinates for that this has these integrable surfaces that I'm going for. In which case, you actually don't need a action angle transform for your original field. So you could do this in straight field line coordinates sort of along the way by what you really do is you sort of are hypothesizing along the way that the transform that will eventually be the transform for this field you're seeking. That's what I'm going for.
On that topic, I think you can get a nearby Hamiltonian using quadratic flux minimizing surfaces.
That's probably an option, yeah.
But I would say if you're going that way, if you're already finding that nearby integrable Hamiltonian and you have surfaces of that, you could just as easily calculate the quadratic flux through those surfaces, and that would be also a measure for chaos.
Yes, it probably would be.
Outperform that, or like if you're already doing that, if you're already calculating a nearby integral Hamiltonian, then just the difference between that and the field that you actually have is already a measure. And the topological data analysis in the field line coordinates of it's a lot more complicated to calculate.
So it is.
Reason that it would be.
Well, I want to use, so that is certainly the quadratic flux minimizing surfaces are probably one way of getting a nearby Hamiltonian. I still question how well characterized it is as a scheme. So it's one option. At the moment, I'm assuming you don't, like what I want to do, okay, I'll make that more clear. What I actually want to use this for is to seek a nearby Hamiltonian. So the flux surfaces will come for free. So this distance wouldn't be used as a measure of integrability for the actual final field. It would be used as a cost function for me to do an optimization that takes you from your original field to a nearby integrable field, where what you're seeking is that the flux surfaces look like the straight line flux surfaces in your nearby integrable field. And then what I would actually want to do is use the action angle coordinates for that nearby integrable field to rewrite the Poincare orbits of my original stellarator field in its coordinates, so that I can do the field line classification effectively in that set of coordinates. But you could probably equivalently do flux minimizing surfaces as well, and use them as your sort of action angle surrogate, and then do your field line classification in those quadratic flux minimizing action angle coordinates. So it's an option. I'm not certain what is best yet because I've yet to properly test it.
Thank you.
It will be.
I think this is a good time to close off. Really looking forward to where this goes. I will stop the recording now.